Hi guys, in this video I wanted to take you behind the scenes of one of the latest prototypes I've been working on, which is a real analog tachometer. It's controlled directly from your sim racing data using SimHub and an Arduino Pro Micro. It might look simple from the outside, but making this needle move accurately and reliably took a fair bit of circuit design and a few clever tricks. So let's walk through how it all works. Now the tach that I'm using is a real automotive style gauge. These are designed to respond to a pulsed 12 volt signal, just like what you'd see from a real car's ignition coil or ECU. The Arduino, on the other hand, only outputs a 5 volt logic signal. So we need a way to take that low power digital signal and turn it into something that the tach can understand. So let's start with the schematic that I made when designing this circuit, and I'll go over what components I used and why I used them. First of all, we have this component here, which is a transistor. This one is a 2N7000. It's a small N-channel MOSFET that we're using as a switch. When the Arduino sends a high signal, the MOSFET connects the tach signal wire to ground, creating a sharp voltage drop, and that's what the gauge interprets as a pulse. The faster we pulse it, the higher the RPM reading. Now let's talk about the resistors, because they're doing a few very important jobs. First, there's a 1K resistor between the Arduino and the gate of the transistor. This helps limit the inrush of current when the gate switches states and protects the Arduino pin from any spikes caused by the transistor's gate capacitance. It's a small addition, but it makes the signal cleaner and the hardware more robust. Next, we've got a 10K pull down resistor from the gate to ground. That keeps the transistor turned off when the Arduino isn't actively driving it. Without that, the gate can float and cause erratic RPM readings, which is actually what happened in early testing. And finally, there is a 10K pull-up resistor from the 12 volt line to the tach signal line. That keeps the voltage high when the transistor is off, giving us the sharp on-off edges that the tachometer expects. Finally, on the schematic, we also have these components, which are the terminal blocks. I have one for the 12 volt power, one for the switch, and one for the tachometer inputs. We power the tach with a separate 12 volt supply. In my first version, I've included a switch so that the gauge can be turned on and off independently. But in the final version, I'm exploring having the gauge only come on when the Arduino is powered. That would keep things simple for end users. It's also possible to power the tach with a DC to DC booster from the Arduino's 5 volt rail, but I'm a little bit cautious about thermal build-up and electrical noise, especially considering this whole unit's going to be sitting in a 3D printed enclosure. So there's probably a little bit more work to do on that. It's not essential, but it's kind of a nice to have. So here it is, all working in its prototype form. I'm sure you'll agree it's pretty rough, but it works, and that was the most important thing. So you'll notice here that I'm not actually using an Arduino Pro Micro, I'm using an Analogue Mega, I think that's how you say it. I'm using an Analogue Mega because they're just much better for prototyping, there's no soldering required, I can just plug wires in and away you go. Other than that, this is basically exactly the same as what you saw on the schematic. And so what came next was just testing. I hooked it up to the rig, I fired up iRacing, and I gave it a test, and it worked. Now as I said, there was a couple of iterations that I had to do on this. Initially, there was just a 10K pull up resistor, there was no pull down resistor, and the gauge wasn't able to make its way all the way up to max revs. It got to about 7,500 revs, and then it wasn't able to cope, and it sprang all the way back down to 0. I believe there was a couple of reasons for this, potentially. One of them was that the transistor that I'm using is actually quite a cheap transistor, and so it wasn't able to cope with the rate at which I was pulsing, or potentially it was down to do with the gauge. The gauge that I got is actually an AliExpress special, pretty cheap, about £15, and there's a possibility that it was also not able to cope with the pulse sequences that are coming out of the transistor. Moving on to the next stage, which is where I'm at now, and that is the PCB design. Now I'm no expert, and this is only my second PCB, but I've tried to follow best practices that I'm aware of at least. What you can see here is version 1.1 of my PCB, but before I landed on this, I actually sent version 1 of this board over to PCBWay, and we can take a look at them here. Now, I cannot fault PCBWay for their service. I had 10 of these boards made up, and they were delivered from China in about 10 days at a cost of only about £10 or $14 US. And here we can see a board that has some of the components just resting in place and ready to start soldering. So what comes next? Well, I now need to do the same testing with this PCB that I did with the prototype. I need to make sure everything is still right. Then when I'm happy with the outcome, I'll get the version 1.1 boards over to PCBWay for manufacturing. And then it's all about designing the final product. What started as a fun what-if project has quickly turned into something really solid, and while it's easy to get lost in the details, it's these small things, like the right resistor in the right place and the right component for the right signal type and so on, that makes a sim hardware project go from just working to rock solid, and I'm super pumped about it. So that's it for this video. If you have any questions about how it all works or want to see this turned into a DIY kit, for example, let me know in the comments, that'd be really good. And if you could drop me a subscribe for more builds, ideas and releases, that would also be great too. Thank you for watching. See you next time.